Well, let's get started. So we're going to continue on where we left off last week, and just do a quick recap. It's been a whole week in between. So what we did is when we looked at shear, we basically looked for thin wall structures, and we basically said to ourselves, well, let's isolate an element from a structure, and let's basically look at the all the stresses acting on that structure or on that element. We're looking at both the shear stresses, the sigmas or the taus, and the direct stresses, the sigmas. And from there onwards, we said like, well, if we look at sigma, this can be somewhat inconvenience for ourselves. So we're going to look at something else that we define as to basically say, we said like, well, if you have a thick wall structure, then we basically have the variation R in thickness is basically constant. And since we always go from basically forces to stresses, we can always divide a force over an area to get a stress. And if we're basically looking at the same, say, the in-plane stresses, then we can get basically a sigma on tau, the shear stresses out of it. But if we go to a thin wall structure, basically we always said we can ignore the thickness, and if we then would ignore the thickness, then we basically this upper part would be a bit more difficult to, more difficult to understand and do it. So we move away from our stress convention, and we said we're going to go to a shear flow convention, and we assume that the shear stress multiplied by the thickness, that's our shear flow. So the shear flow is then what we have is Newton per millimeter instead of our shear stress that was Newton per millimeter squared, or Newton meter squared, or anything else. Yes?
So it has the same unit as the general stress distribution, so we could maybe treat it that way.
No, the unit is definitely different. So this is per millimeter or per unit length, and this is per unit length squared.
As in the general stress distribution, when you point out some arrows.
Oh, here. Say here.
Yeah. So like.
So yeah, this will be our regular case. So if this was our in our regular case, like with thick wall, say we had a beam, right? It was a cross-sectional area, and we have some force on it. Then basically we create some shear forces in that section, and the shear forces multiplied by the area would be equivalent to your applied forces, the external loads. So in this case, your shear forces multiplied by your area, that will be your, say, your vertical force V.
So generally speaking, if you're designing something,
yeah,
should we design based on the shear flow or the shear force?
You always design based on stresses, because that's the material property you can have that gives you failures. So the analysis method, instead of going with stresses, we go with shear flows, and then we can still multiply, because once we have a shear flow and we multiply by thickness, then we still get our shear force.
Divide by thickness.
No, we're talking about shear force right now, right? So this was tau is Newton millimeter squared. Q is Newton per millimeter. So if you do Q times T, you get newtons. So this is shear force, not shear stress. So yeah, okay. So if you divide again by the thickness, then you get your shear stresses out of it. That basically you can compare to your material property X, Y, and Z. So this is how we start with it, and then we basically said, okay, well, especially with thin wall structures, say. We have an I-beam where the flanges and thickness is significantly smaller. Then instead of working with this shear stress going through the thickness, we're going to work with the concept of shear flow, which we defined as shear force, shear stress multiplied by thickness is our shear flow. So that's where we start. Now we did basically the equilibrium equations, and then we recalled from the equilibrium equations, we realized the following. It's basically that we get dq ds plus t d sigma z dz is equal to 0. And this we already basically identified in bending. So we knew that this is a function of the moments. And what we did is we related the moments to the shear forces. I'm going to call those V for now. And then we plug this relationship back into this one. And when doing that, we basically obtain our solution or our equation that relates the shear force V to our shear flow Q. And that relationship looks as follows. So what we get is Q is equal to so we've got this S stands for the shear flow, shear force in the x direction. So say horizontal shear force. Sy is the shear force in the y direction, so vertical shear force, and then Ixx, Iy, Ixy, and Iyy are our moment of inertias of the cross section. And then we have a second part to it, negative. So Sy, Ix, Iyy minus Sx, Ixy, and then zero to S, Ty, ds. So that will be our most generic form of our shear force and shear flow equation. So basically this relates our shear flows to our shear forces Sx and Sy. And once we have our shear flow, we can basically multiply by thickness to get force, if you have a force to design for, or we divide by thickness to get our shear stresses, and then we can see if it fails or not. So that's the steps that we think of. Of course, if we have a symmetric cross section, the previous things that we stated for bending are still true. So if we have symmetry, then Ixy is 0, so this reduces significantly. And then, of course, in most problems, only Sx or Sy given. So then we reduce it even further. So, what's the difficulty in this problem with shear flows? The difficulty does not come from your moment of inertias, because that's what we already did. That's your cross-sectional properties. The shear forces are given 9 out of 10 times. Sometimes it's a moment given, and you have to basically derive a shear force out of that by just looking at what arms are is. So the difficulty from a shear force problem is the integral formulation or solving the integral part. So we have a couple of key components in it. First of all, we're doing the integral from 0 to S. Multiply by thickness, that's relatively straightforward, x ds. So now it becomes, the question is, so what is S? S, so it's lowercase s. And how do you define our x and our y location? So those are the key components that can basically throw people off when doing a shear flow problem. And we had a small problem given a Z section. We were defining 4 coordinates, 1, 2, 3, 4, 4 locations. We know that this is h over 2. The height is h, and this part is h over 2 as well. Centroid lies in the middle, and our axis and y-axis goes from there. And we also say in the problem is that our shear force acts through the shear center. So you see, Sy x and that's important. I will come back later on this lecture why that's important. So with that said, we basically know that a problem doesn't give you an Sx, so we can ignore Sx. So this part is 0, and this part is 0. So this minus minus becomes a plus, and this remains a minus. So we can reduce it a bit, and what we get is that our shear flow problem, Qs is equal to Sy Ixy over Ixx, Iyy, Ixy. The integral from 0 to s tx ds minus Sy Iyy Ixx Iyy Ixy multiplied by the integral dy ds, again from 0 to s. So this is the equation that we're going to solve. The moment of inertia is relatively straightforward, and I will give them as h cubed t over 3 ix iyy is equal to 1/12 h cubed over 12, and xy is equal to h cubed over 8. So we can plug this in into this equation, and we can simplify it a bit. So I'm going to just continue with the numbers. So if we simplify that, what we can get is, well, we know that Sy appears in both parts of the integral, so we can take that out of the equation. And then we can basically combine Ixy over Ixx Iyy minus Ixy squared and get a number out of that. So if we do that, the equation that we end up with is the following. So Qs is equal to Sy over h cubed, then 0 to s, and then we have 10.32x minus 6.84y ds. So if we actually plug in these numbers slightly differ. You can actually get 10.29 and 6.86. Maxon uses these two numbers. He used probably some rounding off errors. So I'm going to just continue this numbering scheme or numbers. So if you're going to cross-check with the example in the book, you get the same solution. Okay. So let's identify. So what we have here. So first of all, we know that the moment of inertia. So this is basically has a t in it on top. These are all t squared, and we multiply again with t here. So basically those t drop out. That's the reason we don't see any t's in the bottom equation. Second of all, we have an h cubed here, but here again we have a basically product of 2 times h cubed. So that's the reason why you have still h cubed in the bottom. Sy is because it's both on the same side. Okay. So that's why it's sy over 8 cubed. I think last week I struggled with this. I didn't know where it came from, but it's because of this multiplication. So now, the most important part. So what's 0 to s, and how can I find the correct values for x and y? Well, 0 to s is basically the shear flow around a segment, so or a certain path. So in this case, if you look at our structure, we have basically 3 segments: 1, 2, 2, 3, and 3, 4. So we are taking this integral at the 3 different segments, each of them. So shear flow for Q1 is done by the integral from 0 for segment 1, say S1, from 0 to S1. Shear flow in the 2, 3 region is basically the integral from 0 to add S2, and 3, 4 is the integral from 0 to segment 3, or alongside segment 3. So, and that's basically the distance that we travel. So that's the distance of the segment. So those are relatively easy to come by. So we know this distance from 1 to 2 is h over 2. We know that the distance from 2 to 3 is h. And we know that the distance from 3 to 4 is h over 2 as well. So what we're going to do is we can just implement these equations and evaluate this equation at all the 3 segments. We're going to start with section 1 at point 1, and we're going to go from 1 to 2, from 2 to 3, and from 3 to 4. And the reason, or we can go from 4 to 3, 3 to 2, and 2 to 1. The reason is why one or the other is you want to always start at a location where the forces and shear flows are known. So in this case, we have a free edge. Therefore, we have 0 stresses, 0 shear flows. So the shear flow at 4 and at 1 must be equal to 0. That gives us the perfect points to start off with. With that said, so how can we define x and y? So x and y are the coordinates, how they vary along this path, along the segments. So for segment 1, 2, see, okay, I have more space on that side. I'll try it right here. So let's have a look at segment 1, 2. There's 1, 2. Okay. So what do we know about the y coordinates, since that one is an easy one? So we start at y here, so that's negative h over 2. And the y coordinate does not change as we move along our path. So our y coordinate remains negative h over 2. Does that make sense? Okay, because that doesn't change. We remain a flat section. So what happens to our x coordinate? So we can divide, what we can actually say, if you actually add one more step to it, we can say y at point 1 is equal to negative h over 2, and y at point 2 equals to negative h over 2. So because of that, it doesn't change, so y is a constant. So if we do the same for x, so x at location 1. So the x coordinate is negative h over 2, right? Negative h over 2. And x at point 2, the end of our segment, corresponds with our origin, so x is 0. Copy this up here. We set segment 1, 2. y1 is equal to h over 2. y2 is negative h over 2. And then we have x1 is equal to negative h over 2. And x2 is equal to 0. So we now need to do, since we define these coordinates, we basically have to make a function of y as a function. We need to find y as a function of s, and we need to find x as a function of s. Since y is basically constant, we know that this one is not a constant, not a function of s. So y remains at h over 2, negative h over 2 to be exact. For x, so we're gonna basically move from 0 to s, and we go from negative h over 2 to 0. So what's that function look like then?
Just be x equals negative h over 2.
Sorry?
Oh, you're just calling it h over 2 distance, right? So
yeah.
We just call x equals h over 2.
No. So we started, so basically what you have to do is like we started, so this is segment 1, location 1. Let's put it in coordinates from 0 to s. That will be at x is equal to 0, you have h over 2, negative h over 2. And at x is equal to s, you have 0. Think, but let's define like that.
So yeah, you're just going to take the integral, and at the end you should just get h over 2 because there's a 0, right?
So we get
plus s1.
Plus s1. Negative h over 2 plus our integral of s. In this case, let's call this, you can call it s1, s1, 2. It doesn't really matter as long as you're remaining consistent. So I prefer to always give the segment numbers, so call it s1, 2. In the books, they will call this s1, this they will call s2, and then this one they will call s3 from segment 1, 2, and 3. But you can define s1, 2, s1, etc. Okay? So this will be your function of s, x of s. So now if you basically plug in, and we know that our s value as path from segment 1, 2, so s1, 2 goes basically from 0 to h over 2. Because this is basically the absolute values of how much you travel. So if we go from 1 to 2, we travel h over 2. That's the distance that we cover. So if you now plug this in, at x is s1 is 0, plug this in, we get negative h over 2, which corresponds to our 0 location, or 1 location. And if you plug in our travel distance of h over 2, then we get our x2 location, which is equal to 0. So now we know that at this location, this is the correct function that we have to deal with. So here, we realize that h over 2 plus s1, 2 is our function. Did this make sense? Because this is basically where majority of the errors comes from, is basically defining your x and y location. And this is a relatively simple problem, but it can come later on, it will become a bit more complex. But once we have done this, we can basically plug it into our integral and just evaluate the integral. So if we plug that in, what we get is Q1, 2, and again, that's remain consistent with segments 1, 2. So this is the variation of the shear flow between segments 1 and in segments 1, 2. We get Sy over h cubed from 0 to h over 2, because that's the segment that we travel, the length of the path s. And here we get 10.32 multiplied by h over 2 plus s1 minus 6.84 multiplied by negative h over 2 ds. And then we can basically plug this in. We can evaluate it. So we basically get negative 10.32 plus 6.84. So that gives us, you see, it's over 2, sorry. So 5.2 15 minus 3.4, 3.4, 1.6, 1.7 here. Okay, so we get this sy over h cubed, again from 0 to h over 2, and then we get 10.32 s1 minus 1.74 h. This h carries over from this. Basically, that's the difference between 10.32 multiplied by h over 2. So negative 10.32 over h over 2 plus 6.84 multiplied by h over 2. So we left over 1.75 approximately h. So we just now have a very simple integral to evaluate. So if we evaluate this integral, we get sy over h cubed. This becomes s squared over 2. So 5.16 s1 2 squared minus 1.74 h s1, and this is evaluated from 0 to h over 2. And what we can do is, if we fill in 0, we get our location 1, and if we fill in h over 2, we get our location 2, right? So what we can do now is, we can define, so we define q at s is equal to 0. We define that as q1, and s equals to 0, and then at s equal to h over 2, we define that as q2, and that's equal to 0.42 sy over h. So a couple of things. So we define, this is the shear flow along the path 1, 2. So the shear flow variation along 1, 2. And once we plug in the coordinates of 1 and 2, it becomes the shear flow at that location. So here, the shear flow of segment 1, 2 evaluated at segment 0, or at s is equal to 0, is equal to the shear flow at s1, or q1, equal to 0. Here, the shear flow in segment 1, 2 evaluated s is equal to h over 2. We call that q2, and that's equal to 0.42 sy over h. Does that make sense? So there are a couple of things that we have to be careful with, and there can be confusion in the beginning. So this equation as qs gives us the shear flow along that path s. We abbreviate that, or we indicate the different paths we take by shear flow q and then two subscripts 1, 2, 2, 3, 3, 4. And then what we can do is we can evaluate the shear flows at those locations. So then we use a single subscript. So this indicates the shear flow equation along that path, and Q1 and Q2 indicate the shear flow evaluated at those locations. So if you would, this would be Q1 would be 0, Q2 would be equal to 0.42 over h, sy, and then we can evaluate at Q3 and then Q4 as well. And now basically we repeat the same. We start again off with this equation and we repeat the same steps for segment 1, 2, 3. And I will do that as well. So this was segment 1, 2. So what we then do is we'll repeat the same for segment 2, 3. So in this case, 2, 3. So if you evaluate the x at point 2 is 0, x at point 3 is 0, y at point 2 is negative h over 2. Y at point 3 is h over 2. So 0 and 0 becomes very simple. That's 0. It's constant. Yes?
I understand the Q1 is 0 because everything was 0.
Mm-hmm.
About the Q2, so it says 0.42 S1 or S12 over H.
Sy. So this is a capital S. So capital S. This is the applied shear force.
Oh.
I understand the confusion. The lowercase s, uppercase s, and then we have Q's that are like one subscript and two subscripts. So let's do the same thing. So who can give me the equation for y along segments 2, 3? What will be that?
It goes from 0 to h.
0 to h. And what's the equation that defines y along that whole segment?
Is that the Q2?
Yeah, so from segment 2 to 3, we're just looking at the variation of y.
Okay.
So y as a function of s2, so y s2, 3, how does that look like?
Is it going to be the h plus s23?
Not exactly. So we started, this is our basically start point, this is end point, right?
Oh.
And we travel h. So how can we come up with the equation that basically satisfies those conditions?
So y2 plus y3 is going to be negative h over 2 plus h over 2?
Almost.
So H plus S23.
Indeed, plus S23. Because S23, this goes from 0 to h, right? This is our starting point. When we plug in 0, we get our starting point. And we plug in our h, we get our end point.
No, that's h plus s23, so it's negative h over 2 plus
Yeah.
s23.
Yeah,
No,
because that will correspond to our two location, two coordinate system.
But s23 is the same as h.
Yeah, S23 in this case goes from 2 to 3, which is the distance h. So we can plug this in. So we get Q23 equal to Sy h cubed. The integral from 0 to s to 3. Let's keep that as 2, 3 for now. X is equal to 0, so that drops. So we get 6.84 multiplied by minus h over 2 plus s to 3 ds to 3 to be exactly. So are we there? In this case, not. So we still need 1 point to add, and that's basically the shear flow at our starting point, which was equal to Q2. Because here, at segment 2, 3, we don't start with a shear flow that's equal to 0. So we have a known value of a shear flow equaling to the shear flow of point 2. So we must add that to this equation to get a correct shear flow of segment 2, 3. Does that make sense? Perfect. So now we can evaluate this. So what we get is Sy h cubed. We go from 0 to h. Let's put this up a bit here, Q2. And what we get is negative, negative, so it becomes plus. So we get 3.42 h plus s to 3 ds to 3. So this becomes, if we evaluate the integral, oh wait, almost forgot myself, it's 0.422 sy over h. So we just evaluate the integral, so what we get is sy over h cubed we get s to 3 squared over 2 plus 3.42 h s to 3, and we evaluate at 0 to h. Plus 0.42 sy over h.
I have a question.
Yes.
Why did the negative 6.84 not distribute to S23 in the second?
You're correct. Let me see, what did I do? That's negative, yeah. We get negative 6, 2, so we get 3.42. So let's be a bit more accurate. Negative 6.84 over 2, right? You're correct. So I made an error here. So this is not plus. This is minus 6.84 S23. And then you take the interval. And then you evaluate from 0 to h. So again, we evaluate that. We can evaluate Q23 at 0. So we'll get the same answer, of course. And that makes sense. Else we don't have consistency. 1 second. So, and then Q23, we evaluate at h. And in this case, if we evaluate at h, we'll get the same answer. And that's just specific to this problem. Yes?
So we added the Q2 part and the Q23. So is it like,
yeah, you add this Q2 here.
So is it like Q2 or is it like Q1?
No, it's Q2.
So if Q1 was not 0, let's say it was a finite value, we would disregard it and add the Q2 value.
Say, you're saying if Q1 was not 0, what would we do with it? Then we would add, say for example, the structure would be like this, right? We go from 0 to 1. Then you still start with 0 or 4 because you know that the shear flow at that position is 0. Then you can calculate, say you start at 0. You can calculate Q0 is 0, but Q1 is no longer 0. So for segment 1, 2, you add Q1 to it. And segment 2, 3, you add Q2 to it. Segment 3, 4, you add Q3 to it. So you always want to start at a location where you know the shear flow is equal to 0. And we'll deal with what happens if you actually have a closed box and how do you solve that? Because at that location, there is no zero, there's no zero location of shear flow. But we'll come to that in a later lecture.
So does that say at the end there on the last equation plus 0.42 SY over H or SY?
Yeah, SY. So this is basically the location of Q2. So plus 0.42 SY over H. And then if you evaluate it, the same values. So, and then you can do 3, 4, but you can also say based how this problem is, we can use, it's not symmetric, but we can use symmetry to it. We can say that this will go to 0 as well, and it will be the same shape, but then basically negative of Q1, 2.
So only the direction would change.
Yeah. So in this case, so let's summarize on this side of the board. Let's get out. And we know that, so Q1 is equal to 0, Q2 is equal to 0.42 SY over H, Q3 0.42 SY over H, and Q4 is equal to 0. So if we have these values, we can also basically plot how the shear flow distribution looks like. So a key point to understand is though, these values themselves don't give you much information. So if you would just having given these values, you would say, oh, well, the shear flow distribution looks something like this because it goes linearly up probably, then it remains constant and then goes linearly in a linear fashion downwards, right? So that's the reason why we also have to take into account the actual Q12, Q23, and Q34. So if you recall Q12 again, so that was basically like this values. Let me see. Okay, sy over h cubed, and then we had 5.16 s1 2 squared minus 1.74 h s1 2 q2 3 was sy over h cubed. And then we had, if you did the full integral, you get 0.42 h cubed plus 3.42 h s2 3 minus 3.42 s2 3 squared. So if you look at the first one, by looking at it, we can predict how it actually is going to look like, and it's going to be looking like something like this. And then you will start at the same location. This will be a quadratic, and then it goes something like this again. So together with those end values, you know where those where you start and end at, and together with the equations and the form of the equation, like this is quadratic minus, basically you can set this to when it's equal to 0, so you can find that there's a deflection point out of it. This one, you know, it's quadratic as well, and has a higher start point, so you can draw the shear flow distribution. Another point, important point is, say from the shear flow, you also know what the limits are. For example, at Q1, Q2, Q3, Q4, and then you can go, if you have the thickness of the structure equal to T, you can get the shear stress out of it. And more importantly, you can also define the maximum. And by definition, that would always be like through the centroidal axis. So you can evaluate, once you have Q2, 2, 3, you can evaluate instead of 0 or h, you can evaluate at S2, 3 equal to h over 2, because that's the central location, and then you can get your maximum value out of it, which will equal to 1.275 sy over h. And then you can compare those values to your stresses and allowable stresses. So there's another example in the lecture slides. I'll let you guys do that at home, and if you have questions, let me know, and we can go through it next week. It's basically in a half circle, and because I spent a bit more time on this, this radius r and thickness t. You basically have to define the shear flow distribution. So find QS. So I think that's a good problem because it basically forces you to do that quadrant transformation going from x and y to cosine r and sine r. Okay, so do this at home. If you have problems, we can revisit next lectures. Else, we just continue. Okay. Yeah.
You said something about the SY-X of the shear center. You said you'll cover it later.
Yeah, that's what I'm going to get to right now. So, good point. So this is what I mentioned before we did this problem. We said like the shear flow or the shear force acts through the shear center. And that was important. And the reason why that's important is do this. So in all our bending classes, say for mechanics, we said like we have a beam, we have force down, basically. In this case, we have it's a similar case that we're looking at, and we said, oh well, our structure bends like this, right? Classical mechanics of materials. So, but now let's look at this. Say we have cross-sectional beam. Okay, and this side is fixed, and then we have a thin walled. Let's assume it's thin walled. Okay. So if you now place the shear force in the middle, what will happen is that we get our classical bending, right? Our structure bends in a linear fashion. So this segment the plane of our square box cross-section remains plane. It just goes in a linear fashion downwards. Now, say for example, if I move this, I have another beam, and instead of in the middle, I load it on one of the sides, right? I load it here. Actually, we draw this a bit better. Then we have our this, and we have our force in the middle. And now we have the force on one side. So we can tell you how it's gonna look like after bending, after our force is applied.
How many degrees of freedom do we have?
Assume this is fixed, and this can rotate and twist.
Then you have a torsional.
Perfect. Right. So what we get is we get bending because we're pushing downwards, and because we're off axis, we basically twist a bit as well. So in this case, it's something like this. So say if pre-post is a bit twisted as well. Okay. And the reason for this is this was applied in a symmetrical axis, so it got basically no twisting on it, and this was not applied in a symmetrical axis plane. Or a bit more correctly stated, this force was applied in the shear center, this was not. So the shear center is a location where we can apply a force to it, and where we get only bending and no twisting or other forms of deformation. So let's delete this. So we said like shear force acts through the cylinder. So if the shear force acts I will abbreviate from now onwards shear center by CS, by the way. So if the shear force acts through the shear center, then we get only bending. Then no twisting / warping of the cross section. And this is extremely important because it just simplifies our lives significantly. So what can we say about shear center? In some cases, we can very easily detect where the shear center lies, and in other cases, we have to determine mathematically where it lies. So from this one, we said like, well, if you have this corresponds with the axis of symmetry. So if you have double symmetry, then the intersection of the two planes of symmetry will be also your shear center. Otherwise, how we look at it is by looking at the intersection of the shear flows at a certain point. So let's define 3 different structures. And yeah, let's define one here as well. So we have three structures. So from this one, if we would say calculate we have given a shear force and we calculate the shear flows, what we can say is, well, the shear flow is going to move like something like this, right? Going up and then down, going like this. And this one will be something like this. So we notice that all the shear flows goes to this point. So by definition, that will be our shear center. Because if we take basically a moment equation, then all the shear flows will be cancel each other out. Similar here. So the intersection point of the shear flows gives us automatically our shear centers. And here as well. So that's the first way that we always can define a shear center very quickly. By just looking, without even doing any calculation, we can say we know at these four locations the shear flow is 0. So we know there's a path of something in this direction and something in that direction. So with the intersection of those four shear flows gives us our shear center. So what happens if our structure is slightly different? So what if our structure is like this, C-section? And let's give it a couple of names. B and H/2, H/2. And yeah, so we have our centroid somewhere here, y-axis, our x-axis. Then we define 1, 2, 3, and 4. So how can we determine the shear flows or the shear center on this problem? So it's symmetric, so we can know that basically will lie somewhere on this axis, but we don't know where it is. So and to do so, what we do is we have to calculate our shear flows. So first one, step 1. Yes. And step 2 is basically determine the location. So we have to determine the location of the internal shear flows contracting the external shear force. So we do a moment equation. We say that Sy must equal to Qs multiplied by a certain arm E, and in most cases we will use the Greek letter psi for that. So let's do that. Let's do this problem very quickly. So I will just give you, so we know there's only a shear force applied somewhere. Let's call it here, Sy, right? It's symmetric. We have no Sx given, so we can reduce our shear flow equation to a simple form of negative Sy Ixx, the integral from 0 to S T y ds. Okay. And now we have to determine Q1, 2 and Q2, 3, and 3, 4 will follow from symmetry. And the moment of inertia is given as Ixx. So moment of inertia is h cubed t over 12 multiplied by 1 plus 6b over h. And we just plug this in. So let's do Again, the exercise of what, in this case, x, there's no x coordinate, so we just have the y coordinate. So what's the coordinates of y and how does it vary with in segments 1, 2? So that's relatively straightforward. So that's basically a constant which is equal to the coordinate negative h over 2. And our distance goes from 0 to b, right? Because that's our path traveled. So Q12 is sy, negative sy over 12 sy t1 plus 6b h. And then the t's drop. So this t drops with that t. And then y is 0 to b of negative h over 2 ds. So if you just multiply this, this negative h, so Q12, this becomes 6 because there's over 2 here. 1h drops, the negative drops. So we got h squared and then sy 1 plus 6b over h. And then we have the integral let's call this S1. Yeah, because we take the integral, so we just have S1 here, right? And then S1 has to be evaluated from 0 to b. But this is the equation for the variation along 1, 2. So per definition, we know that this is the same. So Q12 is equal to Q23, 3, 4. And we don't need Q3, 2, 3 for this case, if we want to calculate the shear center. And the reason is because we basically want to do a moment equivalence equation, right? So we can choose a location where we determine take the moments around that and choose that as our coordinate system. So for example, if we take point 1 or point, in this case, point 3 for the middle, then shear flow Q23 will go through our moment axis, so those contribution will drop out. So now we can call this distance psi, and then we just basically multiply Q12, and we know that Q34 is the same. So we just need Q12 to come up with this moment equivalence equation. So let's do that. Can do this on this side. So we say the moments caused by this shear flow with respect to this point 0, multiplied by the xi distance from that location must counteract our shear flows, or must be equivalent to our shear flows. So Sy multiplied by psi is equal to Q12, and this varies between 1 and 2 because it's not constant. So it's equal to the equal to this from 0 to b of Q12, and this moment arm is with respect to this point is h over 2. So h over 2. And of course, we need 2 because we use symmetry, so it's multiplied by 2. So now we plug in Q12 that we already had derived into this equation. So we get 2 times 0 to b of Q12. So we get Sy, 6 Sy over h squared 1 plus 6bh multiplied by h over 2 ds. I have to go a bit further to the right. Sorry. 2 times 6. Okay. So let's step back one step to evaluate why we have another integral here. Okay. So shear flow is basically shear force per unit length. So if we multiply by the distance from 0 to 1, then we get our force there, right? And once we have a force, we multiply by an arm to get our moment. And that moment must be equal to the moment caused by the external shear flow. So this part, this is our shear flow over our integral, the path that we travel from 1 to 2 to get our shear force, multiply by our moment arm to get us the moment. And then we just evaluate this integral. And if we evaluate this correctly, and we have an sy psi here. So first of all, we can drop the sy's because it's on both sides of the equation. So we get sy, and then we just evaluate this integral and fill it in, and we get that it's equal to 3b squared over h1 plus 6bh. And that gives us our shear center location. So let's do a couple of steps backwards and explain what we did. So let's get rid of this. So we said the shear, when we apply a force through our shear center, we only get bending. So no twisting and coupling, right? So we also know that our shear force causes internal shear flows. So we also know at the end of the day are basically those two have to be in equivalence to each other. So once we calculate the shear flows caused by our shear force, we can say, okay, at what point do these two equal out? And to do so, we do a moment equivalence study or moment equivalence equation. We say that the shear flow, the shear force acting at a point acting at a distance psi away from our point of interest, that moment must be equivalent to the moments caused by the shear flows around that same point. So that's what we come up with. Psi is equal to 2 times QB, Q12 over 1B over the segment 1 to 2 multiplied by H2. Because we know that a shear flow between 1 and 2, this was our shear force per unit length. So we multiply by the length that travels, but the shear flow is not a constant. So we have to take the integral from 0 to b of Q12 to get basically the shear force in 1, 2, right? And then we multiply that shear force by the moment arm around the point of interest or the point that we picked. It can be at any point to get the moment. And that moment must be equivalent to the moment applied by the external forces. So, and then the question is also, how do we define a positive and a negative moment? So here we define counterclockwise positive. So the external moments causing a counterclockwise moment are positive. So that's the reason why it's positive here. And these ones internally, we also define counterclockwise positive. That's the reason why it's positive over there. Okay. So basically separate those two. We look at it, say if you have an SX, you can have basically coupling of the moments, and you have to basically isolate those from the internal ones to define which one is positive and which one is negative. And once we did that, we can come up with an equation that defines, that has basically Sy on both sides, so that drops out, and then you can get a distance psi to be a certain value. So that distance psi is first of all positive, because we define this to be a positive number, how we define it in our equation. So what does it practically means? So it means if you have a C-section, and if I apply my shear force at this location, Sy, of Si, then my C-section bends and bends only. So this can be confusing because you're basically applying a shear force somewhere else. So if you would apply the shear force here, then you would bend and twist at the same time. You might think that, well, how can I apply shear force in mid-air and still bend? This is just mathematically speaking. So the concept of shear force, or shear center, is in this case more mathematically than practical. So in practice, there must be a load transfer from point to point. So there must be, say, a stress structure transforming the load of, say, this midpoint in air to the structure, else it does not bend. So just keep that in mind. In some cases, some of these examples, when the shear center is outside of your cross-section, we're basically talking about mathematical point of view. Where should I apply my shear force to have a zero twist and twisting coupling? That way I just truly bend, and then I can use my standard equation to see what my shear flows are in the structure. And once I know my shear flows, I can determine the shear stresses. And once I know the shear stresses, I can determine if there's failure or not. Does that make sense? Any question regarding this topic? Okay. So in the next lecture, where we go is what happens if we go to a closed section. Okay. And then we will do a couple more problems once we dealt with the closed section. And then we can do a couple more problems from closed and open sections. If there are any things that are unclear or uncertain about, just contact me, raise your hand during the class, and we can discuss those points. Okay, thank you very much.